In 1977, John Backus, who helped invent Fortran and Algol, this is a bit loud, who helped to invent Fortran and Algol, wins the Turing Award. And when you win the Turing Award, they let you give a lecture. And this was his lecture. Can programming be liberated from the von Neumann style of functional style and its algebra of programs? I really love this title because of the word liberated. I think we should use that a lot more in software. But what do you mean? What is this title? What's the von Neumann style? Well, frankly, it's Fortran and Algol. This paper is actually his apology for helping create them. Today, he would mean C. He means that step-by-step imperative programming, doing one thing at a time, constantly mutating some state to get to an end goal, right? And the most important thing that I really got out of this paper is it's not the functional programming aspects, and in fact, when he says functional programming, he doesn't even mean what we today would mean by functional programming. He means a different thing. But what I really got out of this was that there are ways that we can tear things apart. We can take complicated things, tear them apart into simpler things, transform those simple things using some set to make them more generic, and then put them back together again with some rules. This idea of tearing things apart, transforming them, and putting them together is an algebra. That's what algebra is. It's a set of rules for manipulating things. And he wants to discuss an algebra of programs. And I want to be very clear. Swift is not a functional programming language. And if you try to make it one, then it tends to lead to a lot of headaches. But there are many, many lessons that we have found through decades of research, often in the functional programming world, that we can bring to Swift and that can really help us with. So I'm not going to talk about immutable data. I'm not going to talk about recursion or monads. I'm going to talk about algebra and algebra of programs. We're going to talk about composition. So building things out of existing and reusable pieces is better than building one giant, enormous thing that does just the one thing you want, right? There are obvious benefits of reuse, but really the comprehension of programs, I think, is even more important. Our ability to understand them. There are ways that we can reason about small programs, but it's very hard over large messes of programs. And I think most people would agree with me on that. I don't think that that's a very controversial statement. And in fact, even in 1977, that was not a controversial statement. Everybody kind of knew that. So why are we bothering having this conversation? I mean, we've learned our lessons, right? We know the composition is the way. We use delegates and protocols, and we keep everything. Our bindings are weak, and our classes are abstract, and we don't build these tightly coupled monolithic systems anymore like they used to do in the Fortran days. I mean, our classes, they do just one thing, right? And they do it well. Oh, Rob. No, this is composition, right? This is composition. I mean, look, it's composed of data view sourcing and results updating this and the search bar-ness. And we got to put this stuff somewhere, right? I mean, what are you going to do? Okay, I want to be clear. An object that conforms to a bunch of unrelated delegate protocols is not composition. It is the opposite of composition. You've actually taken things that were intentionally split up into separate protocols and glommed them all back together into one enormous object, right? I see this kind of code all the time. Right, you've got a table view or collection view, and it has a couple of states, right? You've got your logged in state, and when you're logged in, you get all your Instabook tweets or whatever you get, right? And when you're not logged in, you get just this one cell that says, "Please log in," right? Or loading or whatever. And so in each of our delegate methods, we have this little piece of conditional logic, and that's okay. It's okay. It's logged in. It's not too bad. It doesn't bother us too much. And then we need to add searching, right? You know, I have a searching, filtering mode. And, okay, it's not too bad. I guess we can work with that. And then they call you up and they go, hey, what we really want is that people, if they've never logged in, I want them to get some content to kind of get them started, some starter content. But if they have trouble logging in, of course, they should get an error. But if they refresh, then they should get the cached content. And that is when you go through the 7 stages of implementing a complicated feature in this code base. There has to be a better way. Glad you asked. Why not use composition? I mean, actual composition. What would it even look like? How would we know it if we saw it? So, shocking, there is no rule that says that a data source has to be a view controller. That is not a rule. There is a rule that says it has to be an NS object, but we'll get past that someday. But I am free to create a data source that is nothing but a data source. That's all it does, right? And then we could make one data source for browsing state and one for the searching state, one for the login state, and each of these does one thing. It just handles turning row numbers into cells, right? It just bends cells. It's this whole thing. Do one thing, do it well. Anytime you see this kind of repeated logic, right, this conditional logic, conditions may be hiding types. You, in fact, might have two types that you're just switching between. Well, why not make it explicit? Actually split them into two different types. Now, this doesn't save us from all the messy conditional logic, right? There has to be this. These if statements actually do have to be somewhere, because that's the business logic. It handles all your special unicornness, right? Your magical rainbows out. It is going to be messy. Why is it messy? Because humans are involved, and humans actually want messy things. We're very inconsistent. We want kind of all these unusual, weird little states. That's okay. You can put it in one place. It doesn't have to be spread out over every delegate method, trying to figure this out. You do it one time, and I just load the correct data source. Now, when we pull that complicated thing apart, we start to find it's easier that there are these smaller, simpler things involved. Our little house here is very complicated, but it's really just, a triangle and squares and rectangles, right? And then we go, whoa, actually these squares are kind of rectangle-ish in this case, and maybe we could break those out and we can say, well, really it's just lines, right? They're just individual lines that I can compose together, and you can kind of drill down to the point that makes sense for your program and build very reusable pieces that you can think about. So, what do we do? So we broke our big crazy data source, or view controller, into 3 data sources, right? And I want to look at these first 2, the browsing and searching, right? And when you think about it, browsing, and that I mean by searching, kind of filtering, right? And when you think about it, browsing and filtering, it's kind of the same thing. I mean, just one has a filter attached to it. Well, actually, we could say both have a filter. It's just one of them's filter says show everything, right? That's a filter. Okay, well, what could I do about that? I could actually combine them. And maybe I can create something that's a fetch request data source, right? Now I have a very generic solution, right? And then I could just hand it maybe a core data context and say, let's go. And you go, yeah. And you go, no. I mean, it sounds great, but it's never going to work. This will never work because everybody knows that this is how we configure cells, right? How do we configure a cell? Well, you get the model object out, and then you tear it all apart, and you shove it into all of the different cells, right? All the different pieces. And, we could make that a closure and try to hand it in, but it's a lot of code, and it's kind of nasty, and that's true. That's probably not going to be good. There's a reason it's not good. This is not MVC. This is breaking MVC. It's usually because we don't understand composition in Cocoa. Most apps I deal with, they kind of get the idea that there's a model and a view controller, right? Controllers glue together models and views, right? They get that. No, but I really mean it. Controllers just glue together models and views. That doesn't mean that they tear apart models, and it doesn't mean that they poke things in views. They just coordinate, they just get them together, right? It's okay for a view to know how to display its model. So if you think about it, a UI label. The UI label has a model object. Its model object is the string. Now, it's actually quite complicated to display a string. It seems easy, but it's actually very hard. You have to tear apart the string into characters, and then you have to convert the characters into glyphs, and then you have to figure out where those glyphs all lay out. And that's why we all know that whenever you put things into a label, in your view controller, you tear apart the string and get all the glyphs out, and then you poke it into all the right places in the label, right? No, you never do that. Nobody, that would be insane. You just hand the string to the label and say, display it. That's your problem. So why do we suddenly go off the rails when it becomes a person object and a person cell? Why do I feel I need to tear apart a person and get their name and all the different things and put their image in the image cell? Just hand the whole person to the person cell. Say, go for it. Right? That's composition. Let the cells take care of it. This also, huge thing, if there's animations, I've seen so many view controllers that are doing all this crazy work trying to chase animations going on in multiple cells at the same time. Let each cell handle its own animations. If we do that, then all of this kind of stuff, all of this now becomes that. I just say, hey. And once I've done that, I've made that really, really simple. I just say, I'm just going to get the model object, I'm just going to hand it to a cell, then I can make it generic, right? Now I can reuse it. So this has one job. Its job is to convert index paths into cells. And it does it by, in this case, looking up an array. But you could put whatever logic you needed there, and then we can solve it to one problem. So we can do the same thing with the login data source here. I said it just displays one thing, so let's call it that. Make it a static cell data source, right? Maybe we initialize it by handing a cell in and you just say, always give me back the same one. Or maybe you hand it a storyboard and it kind of loads it up, or whatever you want. But you start to tear this stuff apart and you can make them small and simple, and then you can make them generic. And then you can start gluing them back together to solve bigger, more complicated problems. Putting the pieces together, so that whole piece of gluing them together, I think a lot of what makes a good programmer, really good programmer, rather than an okay programmer, is thinking about when they glue all their pieces together, you wind up with all these little corner cases sometimes. Sometimes what you're thinking of, your model or how you've built your objects, they don't quite match the problem. And it's unfortunate, so you wind up with all these little tiny corner cases. And so an okay programmer just kind of hopes that those little corner cases will never happen. Just kind of bets on it. And I see so much code, it's like, well, I'm sure that'll probably never happen. That'll never happen. Because I know how this thing is called. I always know how it's called. Now, but a really good programmer is going to add assertions and unit tests and is going to make sure, right? A good programmer remembers all those conditionals and guards and optionals and all of that stuff. So anywhere that the problem is a bit too big or a little too small. And you can do that. And it's okay. You know, it's pretty good. You get all these corner cases, undefined behavior, so there's all these places things don't quite fit. It's not going to crash if you have all your optionals and guards and the like, but it's not great. How we go from good to great is that we actually make the pieces fit. We actually make them be both rigid enough that they fill up the place, but also flexible enough so that they can make it into the little weird squirrely corners of real programs. And that's what we're going to talk about. How do we do that? How do we glue things together? How you glue things together is a major part, in my opinion, of what defines a programming language, what the natural thing to glue together is. And in fact, that's why we call it a functional programming language. So, I said that Swift isn't a functional programming language. The basic unit of composition, the thing you glue together in a functional programming language is, unsurprisingly, the function. It's right there in the name, right? And there are powerful tools. This is Haskell. And Haskell is a functional programming language. And in Haskell, there are so many tools that make it easy, so easy, to take one function and another function and glue them together. So this, I can take it out. I'm going to go left here. There's no left. But I can just say sum. I have a function called fold right, and I have another function called plus. And I can just glue them together with a starting condition of 0. And now I have a new function. I've created a new function by just gluing together two other functions, right? And this, by the way, is why when Haskell programmers come over to Swift, there's sometimes, oh, Swift makes things so hard, I don't like it. So because they're used to this. This is so beautiful. This is actually a very elegant way of putting things together, but it's not Swift's way. Swift's fundamental way of gluing things together is the type. So, protocols, enums, classes, structs, and these are things that in Swift glue together very nicely. So this is a good example where I'm gluing together sequence and a struct. So I have a protocol and a struct, I'm gluing them together in a way by making one function. I suddenly get all of these other methods come along for free, right? And that's also a very beautiful way to compose pieces together. And that's the unit that we want to think about, is that type. Now, this is just one way to compose in Swift. The other way that we can compose types in Swift is what I call lifting. Well, many people call it lifting, I didn't make that up. So you're probably used to it most with optionals. And an optional is a lifted type into a context. That context is maybe it exists, maybe it doesn't. Who knows, right? That's this little bit of data, this little bit of extra context. So it's a string, it's everything a string is, and a little bit more, right? It's lifted. Lifting a type can make it more powerful. Now I say things like powerful. I say things like strong types, right? People sometimes will throw around strong types and weak types and like, and you know, what's that mean? What's the difference? Think of this Venn diagram of every value the type could possibly hold. Everything. So for an integer, that would be, there are 2 to the 64th possible integers. I mean, it's a big number, but it's actually finite, right? There's only so many of them. We know which ones they are. For a dictionary, it would be every possible key value pair that you could put into that dictionary, right? And the program would compile, right? That's what a type really means. A type is a named subset of values, right? Out of all the values that you could possibly express in the language, there actually are values in many languages that you can't express. There are whole things. In fact, we'll even talk about some. So let's think about every value that would be legal to store, right? That would make sense to store in my program. So imagine I have this thing where I have the current state, right? I'm loading or viewing or editing. So there's 3 states. And I used an int to store that, right? 0, 1, 2. And I'm using a type that can hold something like a quintillion values, and I'm holding 3. That's kind of weak. Or I'm using a string. Oh, come back. I'm using a string that could hold, you know, there's not even we don't have words for how many possible strings there are, right? But I'm holding like 20 different strings for keys. That's really, really weak, right? And does that mean that strings are a weak type? Of course not. There are many things that actually fit with it that are very strong strings, like I want to download text from the internet. In principle, anything that is a string could be a string on the internet. Therefore, that makes sense. I've mapped them one to one, even though I wouldn't necessarily expect all of them, they all could be, right? So that's fine. But if I can count up all of the possible things that should ever go into that string, I'm probably using it in a very weak way. It's not the proper use of a string. So here's the counterintuitive part, maybe. I want to make my types stronger. What I do is I make them smaller. I shrink them. I give them fewer values, so that ideally they have exactly the same number of values as legal values. The more places our types can hold illegal values, the more time we spend writing preconditions and unit tests to make sure that they don't. The more constrained our types, the stronger our types, the more whole classes of bugs are impossible. Stronger types require fewer tests. I would rather code that obviously has no bugs than one because it's so simple and so type constrained that the only possible behavior is correct behavior. I'd rather have that than a program that I've tested a lot so that I haven't found any bugs. So, what does that mean in practice? It means that we need to look carefully and critically at our squishy types and try to make them stronger. Okay. Any and any object are pretty much the squishiest types in Swift. We can have little arguments over whether some of the unsafe types are actually even weaker or not. They're kind of weird types, but definitely these are the big boys, because they are They represent every possible type, or every possible value in Swift. And any object and any are really, really closely related. So I won't belabor any difference between them. So they are the entire universe of Swift values. And that is really rare that you mean that. I mean, you don't mean that. Print means it, right? Well, print literally means anything you hand me, I will print anything. Okay, so print takes any. I mean, it means it. But there's not a lot of other cases where you mean anything. JSON. Yes, again, we seem to talk nothing in Swift except JSON parsing. And yes, I know JSON generates any values, but it doesn't really. That's a broken part of Coco's parsing framework. Not every possible value is a legal JSON value, right? So when you have this string to any, you don't mean that. You mean string to a JSON object, right? We just don't have a good type for it, right? So you're actually using it wrong. So yes, Codable will make this easier, and you'll be able to have stronger ones. And maybe you're going to be stuck with any's if you continue to use the systems that generate them, but you can get rid of those any's as fast as you can. Parse them, turn them into other things, make a stronger type. Don't have string to any lying around as properties. Get it down to really real types. So I say any is the squishiest type out there, weakest type that you could have in Swift. Is there a strongest type? Or does that mean anything? Can we talk about a strongest type? So if type is related to how few values you have, then what's the fewest? And I mean, the first thing that should really spring to mind is bool, right? 2 values. That's pretty strong. But could we have just one value? Could you have a type that only has one value? And the answer is you can. There are in fact 3 ways to do it in Swift. You can have an enum that has one case, you can have a struct that has no elements, and you can have a tuple that has no elements. And that's actually very, very similar to being a struct, right? So they're kind of the same thing. The one that we usually like to use in Swift is the empty tuple. And in Swift 2, this was the strongest type in the standard library. And we in fact give it a special name. This is void. Right? Now, in some languages, this would have been called unit for various other reasons because there's exactly one value, so they call it unit. Makes more sense, but they wanted to, the reason we call it void is because it makes it look more like C. People want to make it look more like C, so we call it void. So when you think about these things that return void, that doesn't mean they return nothing. They return void. They return the empty tuple. Right? That's a real thing. You can actually pass them. You can have dictionaries that have voids in them. I mean, it's all legal, right? Could you have anything stronger than void? Right? Does that make sense? I mean, void has one value, so I mean, what am I left with? 0 values. Can I have 0 values in a type? Yes, you can. And in Swift 3, they added this. This is now my favorite. This is my favorite type in Swift. Never has no values. None. You go, well, that's kind of useless. You can't make one. If you think about this just for a second, think about writing the code that would make a never, that would say, you know, let x colon never equals, what would you put next? Right? It has no cases. There's no, never dot what, right? It has no values. Seems kind of weird. Why do I do this? Why do I do this? So in Swift 2, we had an interesting problem. What does fatal error return? What's the return type of it? Well, in Swift 2, it returned void, right? Well, this causes kind of a weird problem because when I'm looking at, remember, everything returns void. It doesn't return nothing, it returns void. It's just a value, it just returns things. So when I'm in a guard statement and I have to leave the else clause, right? So I either have to return something, right? Well, but if you call fatal error, that technically returns void. Well, then what? But I haven't exited. How do I know that is okay to be there? What magic makes it that legal, but a function call to something else is not legal? And the answer is you had this little thing called @noReturn. It was a little compiler directive. You had to add to it to say, yes, I know it returns void, but actually it doesn't. Already, doesn't it feel kind of weird? It's like, why am I having to have this little, well, but it doesn't, you know. It also had a really weird corner case, which was, what if something, you marked it at no return, and then said throws? What does that mean? I mean, can it throw? Is that actually okay, or it's not okay to throw? Not clear. Nobody knew, by the way. I can't remember if it was legal. I don't know if anybody tried just doing it, but in terms of a language rule, the language didn't really define what that means. It's like, please don't do that. In Swift 3, however, we had a never. Fatal return just returns never, and the compiler can look at this. It can see this is what's called an uninhabited type. And there's nothing magical about never. Never is not like, it's in the standard library, but there's nothing magical about it. You can make your own never. You can make them, call them other things, right? It's an uninhabited type. It just has no cases. And the compiler looks at that and says, there is no way. If you say you return never, I know you can't return because you could never generate one. And so when it gets to that line of code, it can go, I know when I call this code, the next line ain't running, right? No magic. It also opened up the question of, or it made possible, I can say, I return never, and also I throw. Which in fact even makes sense, because I can have a function called like run forever. And what's its return type? Never, but it throws in case there's an error, right? And that's totally natural. And whether you want to do it or not, you can decide, but I mean, it's a totally natural thing to do. It means something, it's easy to read. So that's what I love about strong types. It gets rid of corner cases. It gets rid of magic. So, never is the strongest type. Any can hold anything, never can hold nothing, right? Stronger, though, isn't always better. I said we want stronger types, but I mean, I don't want to go out there and just use never, right? That's too strong. In fact, if I have a programming language that only had any, that was the only type in the entire language, I could do lots of stuff. I'd probably have to write lots and lots and lots of unit tests because the compiler wouldn't be helping me. But I could do it. In fact, that language would be called Ruby. And I'm not kidding. In Ruby, it has one type, any. And you write lots and lots of unit tests. There's a reason that unit testing as a culture and test-driven design, even though it wasn't invented in Ruby, really took off on Ruby. Because it's deeply necessary when all you have is never, or all you have is any. Now, on the other hand, could I create a language that only had never? I've been thinking a lot about this. I don't know if you can create it or not, but you shouldn't. But you definitely couldn't get much done with it. So you want the strongest type you can get away with, but no stronger. Going back to squishy types, after any, dictionary is probably the most abused type in Swift. A dictionary means something. It is an arbitrary mapping of keys to value. Arbitrary mapping. Any legal key should be acceptable, should make sense, right, in your program. So here I am, dict name, dict title. Do we think that any key, the next string, could be anything? And the whole entire text of War and Peace is just a string, could be the key. No, it's going to be phone number, it's going to be address. We know what it's going to be, right? It's a short list of things. Well, that tells us that this isn't a dictionary. It's not an arbitrary mapping of keys to values. This is a struct. We just accidentally named it dictionary. Don't do that. This use of strings this way and other ways is so common that actually it's a special name. I actually thought that the Swift team made up this name until I found out that people have been calling it this for years. It's called stringly typing. This happens in so many languages that people complain about it constantly. Stringly typing. So what does stringly typing look like? I have something like this. I have a switch, kind. It's like a check against start, a check against end, right? And default, if it's something else, I crash. And that is, so I go, oh, no, I'll use constants. I'll just use constants here. It's like, you fixed nothing. That didn't help you at all. The problem is the fatal error. The fact that you had to type fatal error is telling you, your type is not pulling its weight. You've created situations where you said, and then I crashed the program. We would like to not crash the program. No, we fixed this. This is an enum, right? Just use an enum. And the great thing in Swift is I can, of course, make an enum be very stringy. So there's not much excuse not to. What about the lowly int, right? Now, in many cases, int should be an enum. I tend to find actually people get that one. They tend to make ints enums when they should. So that's not what I mean. There's other cases, though. There's times when it's not from a short list of possible enums. It's, in fact, any possible int could be legitimate. And how about this? Is this okay? Well, name makes sense and everything, but okay, so I have this ID. Is an ID an int? Is this identifier an int, really? If I decide, does it make sense to add two IDs together? No. Divide them. I don't even know what that would be, right? Does it make sense to, if I change my mind and I decide I want to use strings instead of ints, or UIDs instead of ints, why should I have to change this all over my code, right? Why does anybody know that I actually stored them as ints? Lift it. I can make a struct, make a type. Now I've given context. I said, yes, it's an int. That's an implementation detail. It's really an ID. And the nice thing about this is IDs have no methods on them yet. I put them on them if I want them. Therefore, you don't get plus. You don't accidentally get all these methods that you didn't really want. And I now can't pass IDs where I meant ints, and I can't pass ints where I meant IDs. This actually came up for me. This comes from real code somewhat, because I want my IDs to go from being ints to int64s. And this became this massive effort to go through all the code, looking for all the places. It's like, well, that int is really an int. Oh, but this int was being used as an identifier, right? And which ones do you change and which ones don't you? But if I'd done that, you change maybe a couple of places where you serialize it maybe, and you're done. Okay. So this, I think, is underused. This is a very powerful tool, and I think it's underused. And not just for ints. You can do it for strings and arrays and dictionaries. Have you ever tried to add an extension to one kind of dictionary? Now, this is legal in Swift 4, and it should be legal. But in Swift 3, you get this error. When you're trying to say a dictionary where key equals string and value, you get this thing, same type of requirement means generic parameter, key, non-generic, and it wouldn't compile. And I'm glad that Swift 4 has made this legal, but you probably didn't mean it, right? Did you really mean to add whatever methods you're going to add here to every possible dictionary of strings to images? You probably, in most cases, especially this thing's called a cache, I'm betting that you have some semantics about that string. Maybe it's a path. Maybe it's an identifier. Maybe, I mean, it could be all kinds of things. But it's not just any random string. You have a meaning. So you didn't mean every possible dictionary of strings to images. You meant the ones I'm using as image caches. Well, again, what do? Lift it. Make it an image cache, right? Now I have a type. Now I don't need weird extensions, I just stick methods on it, and I'm done. And it's not kind of secretly a dictionary. Strong types. Now, as I do a little earlier on, I said that protocols were types. In Swift, they are not. Particularly if they have associated values, protocols are type-ish. They describe types. You can sometimes think of them as is types, like an array is a collection, but it's not quite right. What really it is a protocol describes it, describes the aspects of the type. And they're not really types themselves. This matters. Why do I go on about that? It's because I want strong types, but I want weak protocols. Why do I mean weak? Why would I want a weak protocol? Well, because a protocol, if I think about it, a protocol is a list of requirements. And the fewer requirements there are, then the more possible conforming types, right? It's easy to get conformance to this protocol. I like that. I don't want tons and tons and tons of methods on my protocols. I want a very small number of methods on my protocols, so they're very easy to conform to. So I like that. We don't want to create any more restrictions than we need, than we actually need. There's another thing. What about generics? Generics are functions that return types. It's a little hard to see it because the syntax is weird. The syntax doesn't feel like that's what's happening, but this is really kind of what's happening. Is that this is a function that I pass a type to, and it returns me I said struct, I didn't mean that, I meant type. It returns me a new type. This is a function that runs at compile time. So again, it's hard to think about that. It's like, well, can functions run at compile time? Yes, they can, like this one. We often make the syntax a bit different. The thing is, array itself is not a type. It is it's not a proper type. I can't talk about just arrays generally, right? And that's kind of frustrating. So this should be legal, but it's not. I can't just say array. I can't have, why do I need to know what kind, why do I need to know what's in the array? But I have to tell you. But I never use T. Why can't I do it? In a container, it gets even worse. I have to make the whole container generic, or maybe I have to do type erasure. It gets all crazy. Why do I have to do all that? The fact that, oh, I'll come back here. And this gets even worse when you get into things like collections or anything else. Why do I bother telling you about that? What you can say in the language, what makes sense in the language, influences what you can imagine. And what you can imagine influences what you can build, particularly build cleanly, right? So I bother telling you this. There are other languages where you can talk about array. I mean, you can talk about that. It's called or the first class type, it's called higher order, higher kinded types, right? It's a feature, right? And once you go, once you know that such a feature exists, even though Swift doesn't have it, you can think about, I could talk about these kinds of things. And you can start to create things like that. Let's boil this down to a more concrete example. Here's a thing that I see all the time, right? I see this kind of protocol where, function. I take a username, this string, password string, and get some completion handler. And the completion handler takes maybe a string, maybe an error, right? See this all the time. We can do better. Okay, first thing is, what is this string? What do you mean string? Well, I can kind of see down here that it's token, right? And so I guess I could put a little label on it and call it token, except that this is meaningless in Swift. This is a comment. Swift, this label means absolutely nothing in Swift. You could change it, people can change it every time they call it. It tells you nothing. It's almost a shame that it's there because it just often can create more confusion than it helps, right? So it doesn't help. The real problem is you can also get all kinds of, you can get things that aren't tokens. It says it's a string, but really you meant a token. So what should I do? Well, we'll talk about this. Lift it, make it a token. Okay, cool. Now it's a token. Now you see how I don't have to document it? It's right there in the name. Token. It returns a token. Cool. Still problems. We're passing around this username and password. And we like to pass them, you're probably going to pass them together almost all the time. I mean, together, right? They're probably not very useful by themselves. And what you want then is a username and a password. And so what I really would like is a grammar. I would like to be able to say and in types. How can I do that? Well, we have something called a struct. A struct is an and type, right? If you have a good struct, I should be able to say a credential has a username and a password. It should flow right out of the language, right? The type theory word for and types are product types. Why do we call them product types? Well, because how many values are there? Let's say we have this thing, it's a color, it's 3 different colors are possible, and it could be either thick or not thick, there's 2. How many possible styles are there? 2 times 3 is 6. It's a product type. So structs are product types, and types. So we can go in there and we now take a credential. So that's getting a little nicer. And the thing is, now we can do even more. Because we have an actual type there, we could start to expand. Maybe you have something, maybe you make the credential stick things in keychain, right? Maybe you have it for Google logins and OAuth tokens, and I have a lot more flexibility because I stopped handing around usernames and passwords. I lifted it and created a type. Still there's problems. I have this thing, maybe a token and maybe an error. You see, I said and again. That's because tuples, I told you before, tuples are basically anonymous structs. They're very, very similar to anonymous structs. And so they're and types, they're product types. Do I mean maybe a token and maybe an error? No, I mean, two of those sets, I mean, I could get both, I could get neither, or I could get one or the other. 2 of those make sense. 2 of them don't make sense. And then it's like, what do I do in that case? I mean, do I crash? Do I ignore one? What do I do? Because I never meant that. I should say what I mean. What did I mean? I meant a token or an error. I would like a way in types to say or. How do we do it? And we can say it with an enum. Enum is an or type. And this is a very, very popular one. We all kind of wish it were in Swift, but you know, we hope someday maybe. But it's very, very easy to build. This is it. This is the whole thing. I'm just saying it is some successful value. Here I'm creating context again. It's not just a value, it's like a successful value. Or it's a failing error. Right? Again, it has context. Now, product types, or types, or sum types. Why is it a sum type? Well, again, if I have two enums, and this one has associated data with it, right? So there are 3 possible kinds of squares and 1 possible kind of line. How many total styles are there? 4. 1, 2, 3, 4. It's a sum type. I like to call it or. It's easier to remember. Okay. So now we've created result, and we can put our resulting token. We say we have a resulting token, and yes, now people have to kind of learn that the word result means success or fail. It means that it means a value or an error. But once you now have that little bit of vocabulary, it all reads right out of here. I don't even have to document it. I don't have to tell you anything. And if you write it, if you do this incorrectly, it won't compile. Right? So you know you're doing it right. It is hard to do it wrong. That's what I like. I like when it's hard to do things wrong. Fewer corner cases, fewer bugs. And that, I think, is one of the lessons from functional programming that I think we can bring to Swift. Break apart your complicated things, transform them, make them generic, and then glue them back together to make more complicated things. Break it down, build it up. I think that this is something that both John Backus in the 70s and Krusty today could really agree on. Learn from your elders. Thanks. Yeah, I think we have a little bit of time if there's any questions.
What's your opinion about changing or having a model representation to use for your business logic, and then having a separate model representation just for views?
For the view model thing?
Yeah.
It can be good. I mean, it can be view. Yeah, view models are fine if they give you that. So here's the thing. I often put a lot of that logic that I said goes into the view. Just put it in the view. But it is true. If that starts getting really complicated and you're starting to mix up a lot of formatting with actual display, or if you need to reuse the formattingness, absolutely, a view model is an excellent way to abstract it. But I don't necessarily agree with folks who jump to that immediately and have to create everything as a model and then everything has to have a view model and then everything. So it's kind of overkill. You're creating a lot of types they're not pulling their weight.
Okay. Thank you.
So if you're lifting things as simple as an integer, if you decide to actually use a base value string in those sorts of things, when you actually decide to use what's given by Swift instead of lifting it into a struct.
I mean, what do you mean?
So you were lifting values as simple as
an int.
A struct with one int.
Mm-hmm.
So when do you decide to actually use int instead of...
When I mean an int, when I mean a number, like a count, like how many elements are there? That's an int. Now, and I will say one thing, because sometimes people get confused. I'm not telling you to use unsigned. Do not use unsigned, unless you mean a bit pattern. That's a different thing. We can talk about it. It's called a dependent type, so it doesn't have dependent type, so don't try to use unsigned. But beyond that, if you mean a count, then that's an int. How many things are there? So lots of places, and that shows up all over the place. Yeah. Oh, anybody else?
Similar question. Let's say you have a date object, and the date could either be a full ISO, date, or it could just be a date, time. Is that also kind of the thing? If I want to represent that and distinguish between those two different types of dates?
You have to be really, that's a whole can of worms, because dates are a funny thing, because in Swift, a date is not a date. That's the next talk I'm working on, is a date is not a date. So it's a bit complicated because like a date is a specific moment in time. Versus, do you mean, when you say it's a more complicated, you think it's an ISO data, I mean, that's a string representation. So that doesn't, that's a string. So that's a different thing. You really do need to, you have to have in your head, what do I mean when I'm saying a date? Do I mean what the user would see on their clock if they turn to look at it? Do I mean, what do I mean? Do I mean an absolute point in time that everybody would agree on? And then separate the idea of formatting from the idea of storing. If I'm keeping a date, like a day of the week, a day, like August 14th, 2017 or the like, that's date components is the correct type to use for that. So Swift does already offer that, ways to store parts of dates. But that's really tied to a calendar, right? That only makes sense if I also have a calendar. You can't talk about those arbitrarily, whereas a date, everyone in the universe is separate from relativity. Forget that. But I mean, everyone in the universe should agree on when a particular date happens. But if you do need something that has a specific context that's not one of those, yes, I would create a whole new type to create that context and say, no, I don't mean what Swift means, I mean this other thing. Even if its entire implementation is just, it holds a date, it just has different methods on it. Yes?
Question about sort of when you would go to a type alias for
Never.
Never. Always a type.
Easy. So here's the reason. I want to like type alias. I hate type alias because type alias is useless. So there are a number of us who have pushed for, we would like a new thing called a new type, which comes from Haskell, or something similar to it, that actually created a type and would give you a little less syntax. I do agree, yes, creating a struct creates a lot of, there's a lot of syntax, there's a lot of little typing, right? And it would be awful nice to be able to say, new type, ID equals int, right? And it would be, but the problem with but if it did it the way I wanted it, then that would be a full type. Type aliases are literally aliases. So time interval is a type alias for double. That means that you can do anywhere that takes a double can take a time interval and vice versa. It's just a comment. The trouble with that is that actually is confusing because when you add methods to time interval, you are also adding them to double, right? And so you think you have a type and you don't. So yeah, I lied. There is a time you should use type aliases. You should use type aliases when you have some crazy long generic type. Right, it's very hard to type and type out, especially like closure types. Then it's nice, but only because you're trying to make an alias. You're not trying to make a type. Anything else? Well, thanks. Be happy to talk to anybody later. Have a good day.